You know, when we think about the next great frontier in space, our minds usually jump to Mars, or maybe the icy moons like Europa. But what if the greatest test for our engineers, the real deep space proving ground, is a place we're not even planning to visit? Let's talk about the monumental engineering challenge that is Jupiter's moon, Io.
It's a really fascinating question, isn't it? Io has over 400 active volcanoes. It is, without a doubt, the most geologically dynamic place in our entire solar system. And yet, there are no future missions planned to go there. So let's dig into why this world of fire and ice presents both the ultimate challenge and maybe the ultimate opportunity for the future of exploration.
Okay, so to really get a grip on Io, you have to understand just how much of a weirdo it is compared to its siblings. It's the innermost of Jupiter's 4 big Galilean moons, and man, it breaks all the rules for what an outer solar system moon should be.
I mean, just look at the contrast here. Jupiter's other big moons, they're basically worlds of ice. Ganymede and Callisto are these cold, cratered balls of ice and rock. Europa is famous for that massive liquid water ocean hiding under its ice shell. And then you have Io. It's dense, it's made of rock and metal, and it has the least amount of water of any known object in space. We're talking drier than Mercury. It's a terrestrial rocky world hiding out in a realm of ice giants.
And it is spectacularly active. We are talking about more than 400 active volcanoes that are constantly repaving the entire surface of the moon. This isn't something that happened billions of years ago. This is happening right now as we speak. It is, and this is no exaggeration, the most volcanically violent place we have ever found.
You know, one source described it perfectly. They called it a raging battle between fire and ice. You've got this unimaginable heat from volcanic eruptions sitting right next to surfaces that are frozen solid by deep space. And that constant conflict, that is what defines every single inch of Io.
So what is powering this planetary inferno? I mean, the sun is way, way too far away to be providing any real heat. The answer is all about the immense, relentless forces being thrown around by its parent planet Jupiter. Think about it like this. Io is locked in a gravitational tug-of-war that it can never, ever win. It's getting pulled one way by Jupiter's absolutely colossal gravity and then pulled the other way by its sibling moons, Europa, Ganymede, and Callisto. And this constant struggle is the key to, well, everything.
All right, let's break this down. Jupiter's gravity is trying to lock Io into a nice stable position. But the other moons keep yanking it away, and that forces Io into a slightly oval-shaped or elliptical orbit. So as it whips around Jupiter every 2 days, it gets closer and gets stretched out, then moves farther away and gets squeezed back together. This perpetual flexing generates an incredible amount of friction and heat deep inside the moon's core.
And just to put the scale of that force into perspective, think about this. Here on Earth, our moon's gravity creates ocean tides that rise, about half a meter on average? Okay. On Io, Jupiter's gravity creates a tidal bulge in the solid rock of the moon's surface that rises and falls by 100 meters. That is like a 30-story building's worth of solid ground heaving up and down every 2 days. That's the engine driving all that volcanic chaos. Okay, so we've got this insane tidal heating. What are the direct consequences? Well, from an engineering point of view, this is where the environment goes from just challenging to downright hostile. First off, the temperature swings are just mind-boggling. Most of the surface is in a deep freeze, sitting around minus 130 degrees Celsius. But if you get near one of those volcanic hotspots, the temperature can skyrocket to over 1,000 degrees. Any machine we design to operate there has to somehow survive a thermal difference that would just instantly tear conventional hardware apart. And then there's the chemistry. All those wild colors on Io, they come from different sulfur compounds. You've got yellow sulfur snow, you've got white and blue patches of frozen sulfur dioxide. All of this contributes to a thin, constantly changing, and highly corrosive atmosphere. For any sensitive electronics or materials, it is an absolute chemical nightmare. And get this, Io's volcanoes don't even act like ours. They don't build up majestic mountains. Instead, the crust just collapses, creating these huge depressions called paterae. The biggest one, Loki Patera, is a 200-kilometer-wide lake of churning molten rock. So forget about finding a stable landing site. The ground itself is actively collapsing and melting underneath you. So, just when we thought we kind of had a handle on Io's chaos, the recent Juno mission flybys in 2023 and 2024 revealed a brand new puzzle, one that completely flips our understanding of its geology on its head. So here's the thing.
Io doesn't have plate tectonics like Earth, and we just established that its volcanoes create pits, not peaks. So, where in the world do its massive mountains come from? They're just scattered across the surface, totally isolated, with no connecting ranges. It makes no sense.
And we are not talking about small hills. The tallest peaks on Io can soar up to 18 kilometers high. That's literally double the height of Mount Everest. Something is creating these colossal, lonely mountains through a process that's totally alien to us.
One of the best analogies I've read for the leading theory is that these mountains don't grow slowly over millions of years. Scientists think they are thrust upwards violently and suddenly. So here's the working theory. It's called crustal upheaval. A massive lava flow pools up, creating immense weight in one area. That causes the crust right there to sink, but all that pressure has to go somewhere, right? It gets pushed sideways underground, forcing a nearby section of the crust to just fail catastrophically and get shoved skyward, forming a mountain in what is basically a geologic instant. Imagine a sinkhole opening up in one city and a new Everest just popping up in the city next door. That's the kind of process we're talking about.
So what does all of this mean for the future of space exploration? Well, Io's absolutely extreme environment isn't just a scientific curiosity. It's really a series of incredibly difficult engineering problems just waiting for us to solve them.
You know, we've only had these brief, fleeting glimpses of Io. Voyager 1 gave us the first hint back in '79, and Juno's recent flybys just showed us how much we still have to learn. And yet, the next big missions heading to Jupiter, NASA's Europa Clipper and ESA's JUICE mission are focused completely on the icy moons looking for signs of life. For now, Io is being left behind.
And this table really sums it all up. Every single hazard, the rock tides, the temperature swings, the corrosive chemistry, the unpredictable ground, is a monumental engineering challenge. But solving each one of those challenges gives us incredible scientific rewards. It would teach us so much about how planets are powered from the inside out.
And that's really the ultimate takeaway. We probably wouldn't go to Io to look for aliens. We would go to Io to push the absolute limits of our engineering. It's a natural laboratory for testing materials, new power systems, and advanced robotics in conditions that we can't find anywhere else.
So, Io forces us to ask completely new questions. How do you build a machine that can survive being flexed up and down by 100 meters? One that can be baked and frozen at the same time, and navigate a landscape that can literally erupt into a mountain overnight? The technology we developed to answer those questions, well, that won't just let us explore Io, it'll let us explore everywhere else.